the equation remains the same. So again, we have this equation. Again, we can neglect this harmonic oscillator potential, just written for generality. And we have exactly the same equation in 2 dimensions. And then in 2 dimensions, it's known that the quantum collapse also takes place in the linear version of this equation. And moreover, in 2 dimensions, the collapse is stronger than in 1 dimension. Namely, the critical value of U naught in the 2-dimensional case is equal to 0. What it means? It means that for any positive value of U naught, so for any strength of attraction to the center, even if it is extremely small, the wave function will start collapsing onto the center, and the ground state will never exist. So this is a completely catastrophic situation in the 2-dimensional case. And then a natural question is if we can try to stabilize, suppress the collapse and stabilize the model and eventually restore the well-defined ground state if in the 2-dimensional geometry. And we also, last time we already discussed physical implementations of this model, so it can be implemented by means of several different physical setups. Therefore, the question makes sense. And the formal solution of this problem of the collapse separation in 2 dimensions can proceed exactly along the same lines of the analysis which we developed the last time and discussed the last time in 3 dimensions. Namely, we can look for the stationary bound state as a solution of this equation with some chemical potential mu, and then we can, in order to formally remove the singularity from this equation, we can use exactly the same substitution which we used in the 3-dimensional case, exactly the same because the form of the equation remains the same. So this means that natural substitution is based on the assumptions that we can isolate the singular factor as 1 over r to the power minus 1, and then the remaining radial wave function chi is free of singularity. And indeed, we can easily proceed along the lines of this analysis in 1 dimension, 2 dimensions, of course, similar to what we did in 3 dimensions. So we can substitute these ansatz. We can easily analyze the resulting equation for this non-singular factor chi, and we see that indeed at point r equal to 0, we easily analytically predict this finite value of chi, similar to what we had. It's not exactly the same, of course, as we had in 3D, but similar to what we have in 3D. And then it seems that we have a well-defined wave function. However, unlike the 3-dimensional case, this wave function actually is not physically acceptable. And the reason is that it is not normalizable. The fundamental condition is that if we try to compute the full integral of the density of this wave function, in other words, the norm of the wave function, it must converge. If it converges, then it is a physically acceptable result. In 3 dimensions, with the same structure of the singularity in the wave function, we could easily secure the convergence, because when we take the square of this psi to take the density, the singularity will be r to the power minus 2. And if we perform the 3-dimensional integration, in 3 dimensions, as is commonly known, the Jacobian gives us the factor r to square of r, and then under the integral at small r, we simply cancel this squared singular factor r to the power minus 2, and the natural quadratic factor that we have in the Jacobian. And therefore, the integral safely converges at small values of r, and this solution makes sense. In 2D, we have the same singularity. The square of it, again, will give us r to the power minus 2, but the difference is, in the Jacobian, the radial factor in 2D is not r to the power minus 2, it's r to the power minus 1. And for this reason, if we will try to calculate the total integral, which gives us a 2-dimensional norm, obviously it's given. This is the obvious expressions. This is the Jacobian, which I mentioned, r. Then we still cannot remove the divergence. Divergence will be rather weak, because here we will have r to the eventually when we cancel the singular factor r to the minus 2 and this factor r from the Jacobian, the remaining factor will be r to the power minus 1, but obviously integral of dr divided by r diverges as r is approaching 0. It's a slow divergence, logarithmic, but nevertheless it diverges, which means that exactly the same model with the cubic nonlinearity, while it was meaningful in 3D, in 2D it's no longer meaningful. And the question is, can we somehow introduce different physics into this model in order to provide the suppression of the collapse and the stabilization of this model in 2 dimensions? The answer is, in principle, we can do it, because what we can try to do, we can try to take stronger self-repulsive nonlinearity. And formally, it means that instead of this cubic term that we had in the Gross-Pitayevsky equation, we can try to introduce a quintic term, fifth-order term. In principle, there are physical arguments to introduce it, because it's known that we can consider again the Gross-Pitayevsky equation for the gas of particles. And it's known that, formally speaking, if you take into regard not only binary collisions between particles, but also 3-body collisions, not only 2-body, but also 3-body collisions, formally speaking, they will, in the framework of the mean field theory, they will be described, the effect of the 3-body collisions will be described by the quintic term, fifth-order term, in the Gross-Pitayevsky equation. And now we will see that it's sufficient to stabilize the system against the quantum collapse in 2 dimensions. Okay, so in particular, this is a reference to the theoretical paper, which in a different context analyzed the effect of the quintic self-repulsive term in the Gross-Pitayevsky equation when 3-body collisions are taken into regard. And now we can look at what happens in our case. So this is once again our Gross-Pitayevsky equation. It's written for convenience not in the Cartesian coordinates, but in the polar coordinates r and phi, because it's more relevant to use these polar coordinates to analyze the situation. This is our singular potential. This one is formally kept, but we can ignore it. And then we consider actually to concentrate on the effect of the stabilization of the collapse. We can, so to say, for simplicity, disregard the usual cubic nonlinear term and keep only the quintic term. Physically, in principle, this can be achieved because one can use the effect of the Feshbach resonance in order to completely eliminate the cubic term and focus on the case when we have only the quintic term, the fifth-order term here. And then we can proceed with the analysis of the stationary solution for the wave function of this 2-dimensional equation with the quintic nonlinearity. So it's looking at this equation, it's easy to see that now a natural substitution is one which is written here. So again, we are looking for a solution with the chemical potential mu. Of course, it should be negative to have the bound state. And then, in principle, in 2D, we can introduce, we can try to construct not only the ground state, but simultaneously also the excited states, which excited states are ones which carry the angular momentum of vorticity. So integer L, which appears here, is the integer vorticity, or in quantum mechanics, it's called the magnetic quantum number. And L equal to 0 corresponds to the ground state, to the fundamental state. Now, the straightforward analysis demonstrates that the singular factor, which naturally should be introduced here in order to take care of the quintic term, unlike the cubic term which we addressed previously, it's not r to the power minus 1, but it's r to the power minus 1/2. It's naturally this power, the singular power, is naturally selected if we want to balance the linear and nonlinear terms in this equation. And then for this remaining non-singular part of the wave function, chi with the subscript 2D, 2-dimensional, we can easily obtain this approximate expansion at small values of r. So we see that as at r equal to 0, we have the finite, well-defined finite value of this factor chi. And by the way, this factor u with a subscript L, it is a renormalized attraction coefficient. Previously we had u naught, but now if we additionally have the vorticity gives rise, formally speaking, to the centrifugal force, or it corresponds to its usual potential. And this potential has also, as is commonly known, the structure 1 over r squared, but it is repulsive. Therefore, we have this combination, and situation remains non-trivial, of course, if this renormalized factor UL remains positive. So overall, we still have attraction to the center. Okay, now if we have this structure of the singular wave function, we can immediately substitute it essentially into the same integral that we had here for the norm, but now the situation is much better because the square of psi will not give us now the factor of will give us the factor of r to the power minus 1. It will be the square of r to the power minus 1/2, and then we still have factor r in the Jacobian. Then we will safely cancel two factors, r from the Jacobian and square of r to the power minus 1, that is r minus 1/2, that is r to the power minus 1 from the singular factor from the wave function. Integral now converges because now the singularity is weak enough to allow the convergence of the integral, so everything seems to be well defined. So this may be a solution of this problem. However, in terms of the physical implement, yes, let us discuss some properties first of all of the solution. So similar to what we did just to obtain a very simple analytical approximation for the global wave function, similar to what we did in the 3 dimensions, here we again construct the simplest global analytical approximation, the so-called interpolation approximation. What we do is simply, one can say, juxtapose, as a matter of fact, simply multiply the asymptotic form, actually, this expression, the asymptotic form of the wave function in small values of r, and the obvious exponentially decaying factor at the large values of r, and we can use it as a simplest approximation for the global wave function, and then we can immediately calculate, in this approximation, we can easily calculate the norm of the wave function according to what was discussed a minute ago, and eventually, we will end up with a simple relation between the chemical potential and the norm. As I mentioned already the last time, if we consider families of bound states in a nonlinear model, then naturally this family is characterized by the dependence between the chemical potential and the norm, particularly by this dependence. Okay, and then we can also, of course, we can do it more accurately. We can solve this equation for the stationary wave function numerically without approximations. And then we can present typical numerical results. In particular, this is for this particular value of u naught, it's positive. So in the linear version, it would immediately give rise to the collapse, even if u naught is small. Now in this nonlinear equation, we see that we have a well-defined solution. Chi, let me remind again, this is the ansatz for the wave function. So we have this relatively weak singular factor r to the power minus 1/2 times the non-singular function chi. For chi, we have this numerical solution, and the dashed curve shows the simple analytical solution which I mentioned, this interpolation solution. Although it seems to be very primitive, it gives actually a relatively accurate approximation, as we see. And then we can also construct the family of solutions, and as I mentioned a minute ago, we can characterize the family of solutions by the dependence between the chemical potential, which is of course negative, as we must have the bound state between the negative chemical potential and the total norm. In particular, this continuous curve shows the family of solutions for the same value of u naught, plus 0.05. And this dashed curve is this analytical approximation. Now it's less accurate, but still more or less reasonable as a crude approximation. It is produced by this primitive analytical approximation for the wave function. And also, this is a result. This time the analytical and numerical approximations are very close to each other for the negative values of U naught. Actually, the negative value of U naught seems to be strange, because the negative value of U naught implies that in terms of the underlying equation, we have not attractive but repulsive potential. And why do we have the bound state? This is some peculiarity of the two-dimensional Schrödinger equation, that even if we have this potential 1 over r squared, but with a relatively small positive coefficient, so weakly repulsive, it's a peculiarity of exactly of the two-dimensional linear Schrödinger equation. As long as this coefficient does not exceed some critical value, we have bound state even with a formally repulsive potential. Actually, it's a known effect. It's in a sense, it may be considered to be some, in a sense, it's maybe some artifact of the two-dimensional Schrödinger equation, but mathematically speaking, it's a known property which was discovered quite some time ago in terms of a different problem. And so here we also have its counterpart in our nonlinear model. But today we will not have time to talk to discuss in detail why this apparently strange result happens, even for slightly negative values of U naught, so for the slightly repulsive potential. There are papers in which this strange effect is discussed in detail. So as concerns papers, there is if someone is interested, there is a relatively simple and small review paper where all these details are collected. And now we can discuss another more physically relevant possibility to provide the stabilization of the quantum collapse in the two-dimensional geometry. Why do we need to discuss another physical realization of this idea? The point is that, as I said, the physical realization of the quintic nonlinearity is that we try to take into regard three-body collisions in particles of the Bose-Einstein condensate. And as I mentioned, it's known that it will be described by the quintic term. However, it's known that the full physical consideration of the Bose-Einstein condensate in the atomic gas with three-body collisions demonstrates that actually, if we want to write the accurate form of the Gross-Pitayevsky equation, taking into regard three-body collisions, it will inevitably include also some nonlinear lossy dissipative term. What happens is that the analysis demonstrates that three-body collisions, they also have a chance to kick out some particles from the bosonic condensate into the thermal component of this gas. So at any finite temperature, even extremely low temperature, we still have always a condensed component, the Bose-Einstein condensate, and we have also some thermal component. So that strictly speaking, the ideal Gross-Pitayevsky equation valid only for the zero temperature, but of course zero temperature is not achievable. At any finite temperature, we also have some thermal component of the gas. In many cases, it may be neglected, but still it exists. And the result of the analysis is that if three-body collisions are taken into account accurately, they not only produce this cubic term, quintic term in the Gross-Pitayevsky equation that we need, but it will also produce inevitably a nonlinear dissipative term, which takes into regard the losses, because in terms of the condensate, if the particle is kicked out from the condensate into the thermal component, it simply means that it is lost for the condensate. Therefore, it will be, formally speaking, a nonlinear dissipative term. And of course, then if we include this nonlinear dissipative term, we will simply start to destroy the condensate, and so this, physically speaking, it will not be a relevant model. Now, there is another physically relevant possibility, still to stabilize the two-dimensional situation, and by means, formally speaking, of a different nonlinearity, additional nonlinearity. This is the effect which was already discussed in our lectures in some completely different context, actually in the previous cycle of the lectures. It's the effect of quantum corrections of quantum fluctuations to the mean field theory. So the Gross-Pitayevsky equation describes, it's a semi-classical approximation. So it describes the dynamics of the Bose-Einstein condensate in the gas in the mean field approximation, which essentially means that this is a semi-classical treatment of the gas. Therefore, the wave function psi is still interpreted as a single particle wave function. Now, very long ago, famous physicists, Li, Huang, and Yang, so very famous among them are Li and Yang. So these are people who were awarded with a Nobel Prize for their prediction of the parity non-conservation in weak interactions very long ago. And also quite long ago, in 1957, they published a theoretical paper in which, not in terms of the Gross-Pitayevsky equation, but in terms of the just spatially uniform Bose-Einstein condensate, they considered the effect of correction to the mean field theory produced by quantum fluctuations around the mean field state. Of course, quantum fluctuations always take place, and it may be relevant to try to effectively add a correction from the quantum fluctuations. And the result is then, as I mentioned already, also some time ago, much later, there was a theoretical proposal made by the Russian physicist who is a professor in Paris, in France, Dmitry Petrov, who proposed to introduce this Li, Huang, Yang correction as an additional term to the Gross-Pitayevsky equation. The difference from the original old work of Li, Huang, Yang is that now Petrov considers a spatially inhomogeneous situation in the wave function, which is a function of the coordinates. And the eventual result is written here in the scaled form. If this is the usual cubic term, the correction produced by the Li, Huang, Yang effect will be quartic force power. It seems a little bit strange. Why strange? Because it's, in a sense, it's non-analytical. Non-analytical because the natural form of the analytical correction will be quintic. So one can expect that in the analytical case, the expansion should go in powers of the density. Density is a squared absolute value. Here, this, if we compare this quadratic factor here and the cubic factor here, this cubic factor is non-analytical in the sense that it's not an integer power of the density. It's density to the power 3/2. Nevertheless, this is the result of the analysis. And obviously, what we can expect, we see that this is a self-defocusing term, self-repulsive term. And then it can also produce its contribution towards the suppression of the collapse. Now it makes sense to analyze if it will help us to suppress the collapse in the two-dimensional case. In 3 dimensions, it can be also done, but in 3 dimensions, it's not necessary because we know that the cubic term is sufficient, and then when the cubic term is sufficient, usually this Li, Huang, Yang correction is an extremely weak effect which may be neglected. But if we really need this correction, in 2D we can organize a situation in which this cubic term is very small, and then this additional quartic term becomes essential. As a matter of fact, this may be organized according to the proposal of Petrov as follows. One should take not a single component condensate, but a 2-component binary condensate, so that in each condensate we have the self-repulsive interaction, but by means of the Feshbach resonance, we can simultaneously organize attraction between the two components. And now we can consider the symmetric configuration, symmetric in the sense that the wave functions of both components are exactly equal. Therefore, it's still enough to write the single Gross-Petaevsky equation. We don't need to explicitly write the system of two equations. And then this nonlinearity coefficient sigma will be actually the difference between two original coefficients. One is positive self-repulsion in each component. The second is negative. It's attraction between the two components. Now, one can adjust the situation so that this internal self-repulsion and cross attraction between the two components will almost cancel each other. So sigma will become equal to 0, maybe will be very small. In that case, because by means of this condition, we can almost eliminate the cubic term or make it very small. Then this quartic term, which originally is weak, nevertheless will become important. Okay, by the way, it's maybe relevant to mention that both these famous physicists are alive now, and Professor Young is currently 101 years old. Professor Lee is currently 97 years old. Okay. So how we proceed with the analysis of the two-dimensional situation in this case? Okay, we proceeded. So what we do, we write this two-dimensional Gross-Petaevsky equation, similar to what we discussed already today. We write similar to this equation, which we discussed already. We write it in the polar coordinates because we consider the axially symmetric attraction potential. It's quite convenient to use polar coordinates. So now we have this equation, Gross-Petaevsky equation, written in the polar coordinates. So we have this traditional cubic term plus the new quartic term. Coefficient is 1 simply because we choose this scaling. This is our attractive potential, singular potential. Now we can try to analyze the solutions to this modified equation. Actually, this is a reference to some work where this was done. We performed this analysis with my former 2 PhD students. And this is also, by the way, another, if someone is interested, a reference to another brief review where details were collected together. Now the analysis proceeds by choosing these ansatz. So we will want to find a stationary bound state with a negative chemical potential mu. In principle, as we discussed it already today, we may be also interested to construct not only the ground state, but also excited states with non-zero value of the vorticity or angular momentum, in other words, integer L. Here, R and theta, of course, are polar coordinates. And then, so we substitute the ansatz in this equation, and we immediately arrive at the following stationary version of the Gross-Petaevsky equation. It's an ordinary differential equation. So again, this renormalized coefficient of the attraction to the center is U0 minus the contribution from the centrifugal potential in the case of the non-zero angular momentum. And now what we can do, we can easily analyze the structure of this equation as R is going to 0, and then a very simple result is given by this expression. So what we see here, so this is a leading term. This is already a small correction to it. So what we see that we have again some singular factor times a finite value. So this structure of the total wave function, some singular factor times the finite coefficient, is actually similar to what we discussed already today when we consider the quintic nonlinearity, because in that case we had actually this ansatz. We had the singular factor r to the power minus 1/2, and the remaining factor chi took a finite value at r equal to 0. Now we have something similar, but this singular factor is now different because this factor r to the power minus 1/2 was naturally adjusted to the quintic nonlinearity. Currently, we don't have the quintic nonlinearity. We have the quartic nonlinearity. and another power of the nonlinearity, quartic rather than quintic, naturally selects another natural value for the power of this singular factor, and the final result of this analysis is written here. Now the naturally selected the naturally obtained singular factor is r to the power minus 2/3. So what we see, when we formally had the cubic term, we had the singularity r to the power minus 1. And as I explained it today, this is a physically unacceptable result, because then the wave function becomes unnormalizable. The norm integral diverges. Then, as we saw a few minutes ago, when we have the quintic term, which generates the singular factor r to the power minus 1/2, in that case, everything is safe with the convergence of the norm integral, and formally speaking, we have a well-defined result with a caveat, with a comment that in terms of the application to the Bose-Einstein condensates, it may be not quite physically relevant because it ignores the inevitably existing effective nonlinear dissipation in that case. Now, when we consider as a stabilizing factor the Li-Huang-Yang term, we see that we have the power of the nonlinearity, which is intermediate between two previously mentioned values, between 1 and 1/2. It's 2/3. And now it's easy to understand that if we have 2/3, it's still sufficient for the convergence of the norm integral, because the density square of u will give us singularity r to the power minus 4/3. And now when we should compute the two-dimensional norm integral, we still have factor of r from the Jacobian. And then if we look again at this integral, which gives us the two-dimensional norm, if we look at this integral, right? So we will have the power r to the power minus 4/3 from the square of the wave function, and plus at factor r from the Jacobian. The remain is finally we will have the singular factor in the integrand, r to the power minus 2/3, and with the power r to the power and with the singularity r to the power minus 2/3 is integrable. Integrable. This means that the integral of this singular expression converges at small values of r, so it's physically acceptable. Okay, so this is a more physically relevant solution of how we can suppress the quantum collapse in 2 dimensions and predict the previously missing ground state, which would be well defined. Not only the ground state, but also now, if we want, we can predict actually excited states which carry the angular momentum L. And by the way, here we see that we have, as concerns the possibility to construct, in addition to the ground state, if we also want to consider the states which carry the angular momentum, we see another interesting peculiarity of the situation. Namely, this asymptotic result is valid for all values of L, not only for L equal to 0, this is the ground state, but also to the higher order of excited states, because L actually, L appears here, but only it appears, as a matter of fact, in the form of this rescaled coefficient of the attraction to the center. Explicitly, L does not appear. So this asymptotic form is equally valid not only for the ground state, but actually for all states and for all values of L. And now what we see, we see that as a matter of fact, it predicts a well-defined, normalizable bound state for all values of L. Of course, L should not be very large, because if L will become very large, then UL will become negative, and simply we will not have bound states. So UL should remain positive. But if, let's say, if U naught is sufficiently large and simultaneously we can consider relatively large values of L, for which still this combination remains positive. So we can have actually a finite, but maybe a large number of bound states which carries angular momentum, in addition to the ground state, which always exists. And what is interesting about this? So, of course, the bound states with angular momentum are commonly known in quantum mechanics, but usually in quantum mechanics, if we want to construct in 2 dimensions, the bound state with the angular momentum integer L, it may be positive or negative, formally speaking, then the asymptotic form of the wave function at small values of r should be r to the power absolute value of L. Absolute value because if formally the angular momentum is negative, it of course should be the same asymptotic form. And then, of course, is the integral that converges. Everything is actually the physically relevant situation. It is written in any book on quantum mechanics. Now we see that in this specific nonlinear model, with this singularity, which still is physically acceptable singularity, we see that we can construct the vortex state, or the state with angular momentum, in other words, with this asymptotic form, which is different. As r is going to 0, we don't have the vanishing wave function according to this classical expression. We have the weakly singular wave function according to this result. And still, although it's weakly diverging, density square of this wave function is weakly diverging, it's still physically acceptable because it's normalizable. And now the question is, okay, usually why it's necessary in the classical situation, commonly known situation, why it's necessary to demand that when we have the state with the angular momentum, the wave function must vanish at r equal to 0. The answer is because when r equal to 0, so if we have the angular momentum, it means that in the wave function, we have, in the phase of the wave function, we have this term, L times the angular coordinate theta, right? And now if r is equal to 0, this phase becomes actually indefinite. Why it becomes indefinite? Because it's the same point r equal to 0. Physically, it's a single point, it's the same point. We have, formally speaking, all infinitely many different values of the phase, because each other value of the angular variable coordinate theta will give another value of the phase. So we have the indefinite situation, or poorly defined wave function. Its phase simultaneously must take, formally speaking, all values. And then the only possibility to resolve this contradiction is to say that the amplitude u vanishes. If it's equal to 0, then the phase actually becomes just a formal quantity which may take any value, of course. Now we see that as concerns the new solutions of the nonlinear equations that we discussed now, we still have a possibility to resolve this problem that at r equal to 0 phase simultaneously may take all values in an opposite way. Namely, the possibility is that it's known that if the complex number is infinitely large, its absolute value is infinitely large, actually in the space of two-dimensional space of all quantum numbers, there is all points at infinity which have, formally speaking, infinite absolute value and different values of the argument of the phase. They all are equivalent to a single point. So if we want to suppress, to resolve this problem, that at r equal to 0, we must formally have simultaneously all values of the phase, can be resolved, as a matter of fact, in two different ways. Ways. Either we demand that the density vanishes as equal to 0, alternatively, and now this what happens, the amplitude becomes, or the amplitude, yes, u becomes infinitely large. Formally, it's also a solution of this problem of the indefinite phase at r equal to 0. Usually, this formal possibility is ignored. Actually, formally speaking, it's also a commonly known one, as a matter of fact, because if we look at the Bessel function, which is a natural structure of the wave function in the presence of the angular momentum, of course, the usual Bessel function vanishes with the index L, vanishes according to this expression. But also, we have always a singular Bessel function, which diverges as r to the power minus absolute value of L. It's usually ignored when we try to solve the Schrödinger equation, because if we formally take into this solution with the singular Bessel function, the corresponding integral of the norm will diverge. And therefore, it does not make sense. Now, it converges because it's a singular expression for the amplitude or for the absolute value of the wave function, but integral of it converges, of course, converges. Therefore, it's still physically acceptable. And now, so all this solution of all this exercise demonstrates a rather unusual situation. We may have a physically acceptable state with the angular momentum, but as a solution of the nonlinear equation, not as a solution of the linear Schrödinger equation, which actually is not vanishing at r equal to 0, but it's weakly singular at r equal to 0. It's a physically acceptable exotic form of the bound state with a trapped angular momentum. Okay, now there is another aspect of all this, of the solution of this problem. What about the stability? The stability problem is not quite trivial. So intuitively, what we can expect? Intuitively, it's known that in many cases when we have solutions of nonlinear equations, bound states of nonlinear equations, normally the ground state should be stable, but excited states, such as those with angular momentum or with vorticity, in many cases they may still be unstable. And therefore, it's a non-trivial problem to analyze the stability of all these bound states with respect to small perturbations. So mathematically speaking, one can proceed in the standard way, namely, one should take as a solution the wave function, or as a solution of this Gross-Petaevsky equation, which includes infinitely small arbitrary perturbations. So this is a common factor, the same as we discussed already. The chemical potential mu, L is a non-zero vorticity, or it will be the ground state if L is equal to 0. Then this chi is a radial wave function of the unperturbed state. In principle, of course, it depends on L. And then we can add infinitely small arbitrary perturbation. So the natural form, it's simple analysis demonstrates that the natural form of the perturbation is written here. We have some arbitrary amplitude function V1. It's actually, the implication is that it comes with the infinitely small amplitude. And another infinitely small amplitude function is V2. It's more convenient. It's a well-known possibility. It's more convenient when we write this combination of two terms in the perturbation. It's more convenient to write V2 in the complex conjugate form because both amplitude functions may be, of course, complex. Then we can introduce this perturbation. This is already some expression for the actually eigenmode of the perturbation with an arbitrary integer m. M is independent of L. For any L, we have another independent integer number m. This is the azimuthal index of the perturbation. So for each value of m starting from 0, we may have an eigenmode of the small perturbation. And then the mathematical problem is that we should try to find a solution for this perturbation. Of course, we substitute this expression into our full Gross-Petaevsky equation. Then we perform the linearization with respect to the small perturbations V1 and V2. And this way, what we obtain is written here. We obtain the linearized equations with the small perturbations. They are usually called Boголюбов-Dschang, BDG, Boголюбов-Dschang equations. Okay, and then lambda is actually the eigenvalue of this problem for the small perturbations. So if we have the instability, we will obtain the eigenmode, which will be exponentially growing in time. And this means that the solution will have a lambda, maybe not necessarily real, it may be complex. Therefore, here in this part of the ansatz, it's quite natural to write lambda complex conjugate. In any case, if lambda is a positive real part, both this term will be exponentially growing in time. It means instability. On the other hand, if lambda is purely imaginary, then we will have only oscillations in time, but no exponential growth, which means that if we can if the solution of the Bogoliubov-Dschang equation will produce purely imaginary spectrum set of eigenvalues, we can claim that our underlying unperturbed solution is stable. Now, this, mathematically speaking, this system of coupled Bogoliubov-Dschang equations is some mathematical problem for what is called for the eigenvalue problem, because we need to solve it, and so that to find the eigenvalues lambda appears on the left-hand side of the system of Bogoliubov-Dschang equations. Of course, it seems that it's a rather difficult mathematical problem, because it's, of course, this a system of linear equations. However, it's definitely not easy to solve it because we have variable coefficients. So this coefficient depends on R, and this coefficient has its own dependence on R, and also this one depends on R. So, of course, definitely we cannot produce a full analytical solution of the system, and in principle, one should try to solve it numerically. And quite surprisingly, eventually, the condition which distinguishes stable and unstable situations, so the situation when we have purely imaginary lambda, or at least one eigenvalue, which is complex and therefore gives rise to the instability, this solution of the instability problem can be obtained in a fully analytical form in spite of the complexity of the system of Bogoliubov-Dschang equations. Why it's possible? It's possible because one can try to simplify the analysis in the following way. One can focus on the case when the new eigenvalue is going to appear. So one can try to identify the bifurcation. The bifurcation is some values of the parameters. As a matter of fact, the control parameter is U0, the strength of the attraction to the center in the underlying problem. And so, because as I said, this coefficient chi0, let me remind, we found it. It was a part of the solution. It was this coefficient, as a matter of fact, this coefficient. So the only free parameter here is U0, and of course, L is also a free parameter, but it is a parameter which takes only integer values. The parameter which takes arbitrary, continuously varying values, this is U0. Okay, so we can try to identify some value of U0, so that in this critical value of U0 for given L, we have a new eigenvalue with some particular integer value of M of this index, which is going to appear as a relevant eigenvalue of this system. So this analysis of the bifurcation where the new eigenvalue appears can be performed analytically after some efforts. And it gives rise to a surprisingly simple result. And the result is that the first new, if we, it's better to say this way. Let us say that we take originally very large values of U0 and then start to decrease U0, make them somewhat smaller. So if we are following this this line of the analysis, we will see that there is some critical value of U0 when we decrease U0, and at this critical value of U0, a new eigenvalue will appear. This is what can be done analytically. So this critical value of U0 is written actually here. It's this relatively simple expression, 7/9 times 3L squared minus 1 for given integer value of L. Of course, it should be positive, definitely, by definition. So it makes sense for all non-zero values of L. For L equal to 0, formally speaking, it's negative, which simply means that such a critical value does not exist for L equal to 0. So this is the analytical result. Now, the remaining part should be done numerically, and the full numerical solution demonstrates that indeed, when U0 is larger than this critical value, the spectrum is completely stable. It includes only purely imaginary eigenvalues. And exactly when we pass this critical value, when we take U0 smaller than it, we will have the first new solution for the eigenvalue, And this solution will, it will be a pair of solutions actually, and this pair of solutions will introduce instability. So therefore, although the full system of the Bogalubov-Dschang equation is a challenge, it's quite complex, nevertheless, the problem of identifying the critical value of U0, which is a boundary between stability and stability, can be solved in a fully analytical form, and this analytical prediction can be eventually verified by means of direct numerical simulations. We can take this solution and try to simulate its evolution in time, its percept evolution, and we will see that when U0 is larger than this value, indeed, it does not develop any instability, but when U0 is smaller, I will now show an example, it will develop an instability. And okay, so in particular, if we take the simplest solution, which may have the instability with L equal to 1, so we see that the instability will appear when it's written here in the opposite form, the stability condition. When U0 exceeds this particular value, this vortex state, bound state with L equal to 1 is stable. If U0 takes value below this particular value, it will be unstable. And then another question is, what will be the value of this integer azimuthal index m, which corresponds to this newly appearing unstable eigenvalue? The answer is that this integer in azimuthal index of the perturbation will be plus minus 1. It should not be 0, it can be plus minus 1. And now what it means in terms of what kind of instability can it predict? If we have m larger than 1, which gives rise to the instability, for example, 2, it means that it will split this axially symmetric bound state into, it will break the axial symmetry. It will break this axially symmetric vortex bound state into 2 fragments. And if m takes still larger values, 3 and so on, it will break, such an instability would break the axially symmetry, it would break the axial symmetry or the rotational symmetry, and instead of this axially symmetric bound state, we would obtain a set of fragments. The number of fragments will be equal to m. Now, if m itself is equal 1, plus or minus 1, of course, we cannot talk, it does not make sense to talk about the breakup into a single fragment. What actually happens in this case is this instability mode means that the bound state, this bound state with the vorticity is not broken, but it starts to perform a drift. It leaves the central position and starts to perform the drift motion from the center to periphery. So here is an illustration. This is what is shown is the coordinate of the center of this unstable vertical bound state. Originally, it was positioned at the central point, and now we take this numerical solution for U0 equal to 1.53. This is slightly smaller than this critical value which I mentioned, at which we have this instability boundary. So the numerical simulation with U0 larger than 1.56 will simply demonstrate indeed the stability of this bound state with the vorticity 1. But when we take this particular value, 1.53, we see that the central point spontaneously starts to drift at the direction of the instability, starts to drift along this spiral trajectory. So it will be eventually, it will perform many cycles of the motion with a very slowly increasing radius. So it moves along the spiral, and eventually, because for the stability of the numerical scheme, it's necessary to perform the simulation with artificial absorber for perturbations, which is installed at the boundary of the integration domain, far from the center. If everything is stable and the ground state remains, the bound state remains stable, the absorber does not produce a strong effect on the form of the numerical solution. But if you have any kind of instability, the absorber is gradually eating the some wave functions which are emitted by this unstable solution, and therefore if we can follow the evolution of the total angular momentum of this vortex state, and we will see that gradually the angular momentum will be decaying, as we see here, because when this drifting vertical bound state will come too close to the boundary of the integration domain, it will eventually hit the position where we placed the absorber, and it will be the angular momentum will be actually eliminated by the absorber. So the final outcome of this instability is that when we start from the unstable bound state with vorticity, the pivot of the vortex, the central port of the vortex, will be actually ousted along this spiral trajectory. It will be ousted from the center to periphery, where it will eventually disappear because it will be killed by the absorber, and we will have spontaneous transformation of this state with angular momentum into the fundamental bound state with zero angular momentum. Okay, and now we can, one more thing that we can now consider. Let me apply zoom here. Okay, so let us now get back to the three-dimensional case. So in 2 dimensions, we could see that in 2 dimensions we can analyze equally well both the ground state and the excited state with angular momentum. Now, when we did the analysis in the three-dimensional case, we only considered, as a matter of fact, we only considered the states with the ground state without trying to construct a solution with angular momentum. It's still interesting to see if we can construct stable bound state with embedded angular momentum in the three-dimensional case. So this actually situation was analyzed quite recently, and we can again look at our Gross-Petaevsky equation. So this is again the three-dimensional Gross-Petaevsky equation that we already discussed many times. So this is our familiar parameter U0, the coefficient of the attraction to the center with a singular potential. And this is our cubic nonlinear term. So it's formally speaking a simple Gross-Petaevsky equation, although it may produce many non-trivial solutions. And now what we would like to do, previously we analyzed its solutions which were spherically symmetric with a full three-dimensional isotropy, and they would represent the ground state which replaced the collapse. And now we would like to try to find the solutions which would demonstrate not the spherical symmetry but only cylindrical symmetry, only axial symmetry. The symmetry will be reduced because we will try to introduce the vorticity. Obviously, the vorticity reduces the symmetry from three-dimensional to two-dimensional. Okay, so mathematically speaking, we want to look for stationary wave functions as solutions of this equation in this form, and for function u, which is still complex. We don't assume it to be real, because if we want to have the bound state with angular momentum, of course, the wave function still should be complex. So we obtain this stationary version of our Gross-Petaevsky equation, and again, we will characterize the bound state, if we are able to find one, by the total value of the norm. Okay, then it's also, because we're talking about the angular momentum, of course, it's also relevant to define the total angular momentum of this configuration, if it does have the non-zero angular momentum. Previously, when we worked with the ground state, of course, it had zero angular momentum. Now it's not. We are going to construct states where it will not be zero. So this is a standard expression which gives us a three-dimensional integral that defines the total angular momentum of the bound state. And also, we have the dynamical invariance in this equation. One is, of course, one dynamical invariant is a total norm. The vector of the angular momentum is also a dynamical invariant. And the third dynamical invariant is the energy or Hamiltonian of this equation. The energy is written here. Okay. Now, to try to analyze the possibility of constructing the wave function with the angular momentum, it will be quite natural to rewrite this our original Gross-Petaevsky equation. This is exactly the same equation, but to rewrite it instead of the Cartesian coordinates in terms of the three-dimensional spherical coordinates, or sometimes it's called three-dimensional polar coordinates. So this is a standard set of three coordinates: r, the radial coordinates; theta, the azimuthal. And we have two angular coordinates, theta and phi. So theta varies between 0 and pi, and phi varies between 0 and 2 pi. So this is a standard. We substitute the standard form of the Laplacian written in the three-dimensional Laplacian written in the polar or spherical coordinates, and we immediately rewrite our equation in this form. It's exactly the same as the original one, but as I said, it's written now in terms of the polar coordinates, and actually this term U0 still represents our singular attractive potential. Okay, then if we explicitly want to construct solutions with angular momentum, so we should introduce the integer vorticity m. In terms of quantum mechanics, when we try to find a three-dimensional solution of the linear Schrodinger equation with the angular momentum, in other words, with vorticity, this vorticity is quantified by the integer quantum number m. This m quantum number, usually in quantum mechanics, is called the magnetic quantum number. So then we specify a particular type of the solutions that we would like to find as a solution to this full Schrodinger equation. So we have is a bound state with some chemical potential mu, which should be negative, of course. Then we explicitly write in the phase this term, which reproduces the angular momentum of vorticity. Integer m times phi is this polar coordinates, and then there remains factor, which is the remaining part of the stationary wave function. It will be naturally a function of two other coordinates, r and theta. Now we substitute these ansatz in our three-dimensional equation and obtain the simplified equation only for function u. And by the way, as concerns the complexity of the phase, all phase is represented by this factor. So the remaining factor um may be assumed to be a purely real function. Therefore, this equation is now written as the equation for the purely real function u with the subscript m. Okay, so now what we should try to do, we should try to solve this stationary nonlinear equation. Mathematically speaking, it's a nonlinear partial differential equation with two independent variables, two coordinates r and theta. Therefore, it's still quite a non-trivial problem. And again, what we should try to do, we understand that because of the presence of the pull to the center, our singular potential, of course, the wave function should have a singularity, a singular form as considered as r going to 0, and we should expect that naturally it should be exactly this. We should be able to isolate exactly the same singular factor that we had when we analyzed the ground state. The factor is r to the power -1. It's the same universal singular factor for all solutions, irrespective of the presence of the angular momentum. So what we can do, we can to isolate the singularity, we substitute in this equation for u these ansatz r to the power minus 1 the singular factor times the non-singular factor capital V. It's also a real function, it's a function of m. So the result of the substitution is written here. And now we will have to try to find a solution of this nonlinear partial differential equation, which will be free of singularity at r going to 0. And let me remind that if we have this singularity, it's acceptable because, once again, if we will eventually try to construct the norm of this wave function, a three-dimensional integral which gives a norm with this singularity will be converging, and therefore it's a physically relevant singular wave function. Okay, so now the mathematical problem that we should try to address is to somehow solve this equation and see what we can produce as a result of the solution. Okay. Because we here introduce the ansatz which explicitly separates a singular factor and non-singular one, what we can now it's quite natural to first of all understand this solution for the non-singular factor Vm simply at r equal to 0. Actually, this is very similar to what we did previously when we addressed the ground state. In that case, actually, this factor V asymptotically at r equal to 0, it was simply a finite constant. And we, from our analysis, we could find the exact value of this finite constant, and therefore we could say that this is how the system suppresses the collapse. It replaces the collapse by the singular but acceptable wave function in the form the singular factor times this particular finite constant value of V, and we could find it. We actually have found it explicitly. Now we have a similar problem, but when we set r equal to 0, it's not so simple, because now V still remains a function of the angular variable, angular coordinate theta. Okay, and so this means that what we can do, we can take this equation and just set directly that r is equal to 0 in it. So this means that actually we have one term with
Boris, 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 Boris,
I think Professor Boris did not hear us.
Yeah, maybe I think that he has a problem.
I think he has some internet issue.
Yes, I'm trying to contact him.
Yeah.
Boris,
quantum number m.
No, it's okay.
For
Yeah, it's
given
okay now.
strength of attraction, you know.
Boris, I don't know what happened exactly. Boris,
I mute myself.
Boris.
Can you hear me now?
Yes, for about 3 minutes we could not hear you.
Okay, I will now restore. There was probably some interruption. I will
Yes.
restore sharing screen.
Yeah, yes.
Okay, so we are back in the same position. Let me get back approximately to what we were talking about 3 minutes ago.
Exact.
Okay, so, okay, just to be sure that there will be no interruption, let me say
Yes,
that
yes.
what we're now trying to do, we address this three-dimensional Gross-Pitayevsky equation, and then we proceed to its stationary form. The stationary form is written here. We will characterize the solution by the total norm. Of course, it should converge. Then we also introduce this dynamical invariance of the equation as a norm. The total angular momentum is given by this integral. It's a vectorial quantity. And also, this is the energy or Hamiltonian of this equation, which is the additional dynamical invariant. And then what was convenient to do was to take our original equation and rewrite the same equation in terms of the three-dimensional spherical coordinates, which was done here. And then we introduce this ansatz for the solution. This ansatz implies that we would here we have the set of spherical coordinates r, theta, and phi. And now we explicitly separate the dependence on phi. It amounts just to having the term linear with respect to phi in the phase. So this is the usual ansatz for the state which carries the vorticity, or in terms of quantum mechanics, angular momentum. So m in quantum mechanics, it is usually called the magnetic quantum number. And the result of the substitution is that we derive the two-dimensional nonlinear partial differential equation for this function um. Now this function may be considered to be real because the complex structure is exactly represented by this factor. And then further, in order to isolate the singularity in terms of at small values of r, we apply substitution similar to what we applied when we wanted to analyze the ground state. Namely, we explicitly write the solution in this form. So we separate the singular factor and the non-singular one, v. And so, as we already know, this singularity is acceptable because the three-dimensional norm integral will converge. And then, after the formal substitution of this ansatz into this equation for u, we now derive the equation for v, for this factor in the wave function which does not contain any singularity. And then what remains, we should now, if we want to understand the structure of the wave function, we should try to understand its asymptotic structure at small values of r and at large values of r. At small values of r, essentially this simply means, because v does not have any singularity, we can simply take this equation for v and directly set r equal to 0, which means that we have two terms which are proportional to square of r. They will simply be dropped, and there remains to analyze the ordinary differential equation, because now this function v remains only a function of the single coordinate theta, the angular coordinate, which takes values between 0 and pi. So now to analyze the asymptotic structure of the wave function, we arrived at the necessity to solve this ordinary nonlinear differential equation. So m is, once again, m is the integer number. It is the magnetic quantum number in terms of quantum mechanics. U0 is our control parameter, the strength of the attraction to the center. And on the other hand, because we're talking about the asymptotic structure of the wave function also when r is going to infinity, at infinity, we will have, as usual, for any negative chemical potential, we will have the exponential decay. So it means that our bound state is indeed exponentially localized. Okay, so now once again, the remaining non-trivial problem is to understand what solutions can be produced by this equation, which determines the angular structure of the wave function at small values of r. And okay, so in this case, if we drop this cubic term for the time being, we obtain the linear equation. This linear equation is a commonly known one because it is exactly the linear Schrödinger equation for the three-dimensional linear Schrodinger equation from quantum mechanics. When we try to solve this equation with the non-zero value of the magnetic quantum number m. It is commonly known that in quantum mechanics, the full set of bound states of such solutions is characterized by a set of two quantum numbers. We introduce a quantum number which is usually called L. This L is called the orbital quantum number. And then we can have solutions when m, the magnetic quantum number, takes all values from plus L up to minus L. Okay, so now we should, now of course we don't solve, we are not trying to solve exactly the same equation because this solution is written in any textbook on quantum mechanics, but now we try to solve it in the presence of this additional cubic term, nonlinear term. But still it will be quite relevant to try to parameterize the solutions by exactly the same set of two commonly known quantum numbers, L and M. And first of all, we can try to construct the simplest possibility is to construct particular solutions when M is equal to L. In quantum mechanics, usually such bound states are called by the traditional name for them, sectoral bound states. So sectoral bound states are states with the angular momentum when the two quantum numbers are equal to each other. Okay. So then we can see that this equation, it's natural to look for solutions to this equation when, so theta, the angular coordinate, varies between 0 and pi. And first of all, it's natural to look for solutions which satisfy these boundary conditions at these 2 points. When theta is approaching 0, we can find the solution which vanishes as theta to the power m, and simultaneously when theta is approaching pi, the same solution should be vanishing as pi minus theta, also to the power m. And this possibility suggests us, first of all, to try to construct a solution when its amplitude is very small. If it is very small, then in the lowest approximation, we can still neglect the cubic term, and then we get back to this equation, linear equation, whose solution is very well known from quantum mechanics, and the solution is written here. So this is the solution. So in this case, this means that we have the constant amplitude V0. We consider the formula V0 as an infinitely small amplitude of the solution, and then for this infinitely small amplitude, we have actually an exact solution. Of course, it's a solution which is borrowed from quantum mechanics, and in terms of standard notation adopted in quantum mechanics, it corresponds to what is called the spherical harmonic capital Y with equal indices L and M are equal to each other, so LL. Oh, so now L and M are the same. Okay, and now, but the question is, okay, we have this, we want to have this exact solution for the linearized equation for some, but it will depend also on this coefficient U0 in the linear part of the equation, because we introduced it as a control parameter of our system, is the strength of attraction to the center. And then if we substitute these answers for the solution, for the linearized solution, we immediately arrive at the conclusion that it is indeed an exact solution, but only for the some special value of U0, for some threshold value of U0, and this threshold value is quite simple, m times m plus 1, or because this is what is called the sectoral quantum mechanical state, we can say that L times L plus 1. So this combination, L times L plus 1, is a commonly known expression in quantum mechanics because it determines essentially the eigenvalue of the kinetic energy of the bound state of a quantum particle which carries the angular momentum. So the eigenvalue of the square of the angular momentum, essentially its kinetic energy related to the angular momentum, is commonly known that this eigenvalue will be L times L plus 1. So now we naturally arrive at this expression, and it will give us the threshold value of U0. And the meaning of this is As a matter of fact, we want to solve, of course, the full equation, which includes a nonlinearity. It means that the solution which we want to find of this type, it appears as a solution with an infinitely small amplitude as a bifurcation point, at the threshold value of U0. In other words, when U0 is smaller than this value, we don't have this solution. It simply does not exist. And if U0 becomes larger, the solution develops a more complex form, but it is still close to this expression. And so when U0 becomes slightly larger than this threshold value, we have the branch of solutions, which then the amplitude starts to grow from infinitely small values to finite values. So using these arguments, we want now to construct the solution in this case, when U0 is larger than the threshold value. And so physically speaking, why a solution can exist in this case? Because, as I mentioned already, the kinetic energy of the particle which performs this motion with angular momentum is given by this expression. And on the other hand, so we have the competition, because the kinetic energy implies that this is an energy which actually accounts for the presence of the centrifugal force, the force which tries to actually repel the particle to release it from the bound state. On the other hand, we have the attractive potential, our original attractive potential, with strength proportional to U0, this attractive potential, which tries to keep the particle in the bound state. And this condition, as a matter of fact, implies that the energy of the attraction to the center is stronger, negative energy is stronger than the kinetic energy, which tries to generate the centrifugal force, and therefore the particle is able to remain in the bound state. So this is the condition at which we can try to find the solution. And then to find the solution in the approximate but explicit form, first of all, we can, let us look at, first of all, as a simple situation when this m is equal to 1. M is equal to 1. So the simplest non-trivial case with angular momentum, which is equal to 1. Then we expect that exactly at the threshold, the solution will be simply some arbitrary small coefficient times sine of theta. Let me remind, in the general case, when m is 1 or larger, we have this structure, sine to the power m. Now we have simply the first power of sine. And now if we finally want to approximately construct the solution of the full nonlinear equation, which once again includes this nonlinear term, we can assume, okay, so when we U0, this parameter is slightly larger than the critical value, than the threshold value, we can assume that, as a usual assumption, that the solution will be close to its form when it was the amplitude was infinitely small, but now the amplitude will be finite. Okay, so what it means, we approximately substitute our approximation for the solution, still exactly this approximation, which we borrow from the exact solution with the infinitely small amplitude, we substitute it into the new cubic term. In the cubic term, we will have to somehow take care of the third power of sine. So we use this commonly known elementary trigonometric formula, and then we apply something which may be called the mean field approximation. Namely, we keep this term with sine of theta because it's the same as we have in the linear terms of the equation, and we just neglect the third harmonic. If we want, we can take it into account as small correction to our simplest approximation. So now this threshold value for m and l equal to 1. So let me remind, the threshold value generally was m times m plus 1. Now it will be simply 2. 1 times 2, it will be 2. So now we try to construct this approximate solution in the slightly overcritical case when U0 slightly exceeds the threshold value 2. So the case that we want to explicitly consider is when this U0 minus 2 is a small but positive parameter. And then when we apply this approximation, as I said, we neglect the third harmonic, we collect all terms with the first harmonic, and we easily predict the amplitude of the solution, this we note, by this simple expression. So as usual, we predict that the amplitude grows as a square root of the distance from the threshold point. V naught minus 2 is a parametric distance from the threshold point. And as usual, the bifurcation, or if you want the phase transition, which gives rise to this bound state, has amplitude which grows as a square root of this control parameter. Now we can try to develop similar analysis, but now for the value of the magnetic quantum number, which is equal to 2, vorticity equal to 2. Okay, then it means that when we have the just exactly the threshold, we have the solution with the infinitely small amplitude V naught, and now we look at the general expression. It was sine to the power m, and by the way, this threshold now will be 2 times 3 when m is equal to 2. It means that now the threshold V naught must be 6 if we have this bound state with double vorticity. And then it's natural to look for a solution which approximately will have this form sine of theta to the power m, which means square of sine. Okay, so this is our approximation for the solution. And then in order to handle the cubic term approximately, we again use some trigonometric manipulations. We write this trigonometric identity, and then we say, okay, this is the square of sine, which is essentially the same term that we have in all linear terms of our equation. And these are some contributions from higher harmonics in comparison to our basic term, which in the simplest approximation we may neglect. So we replace the cubic term according to this approximation, and then we immediately arrive at the prediction for the amplitude for this sectoral bound state. Again, it will be square root of the distance from the threshold, but now the distance from the threshold is U naught minus 6, because the threshold takes place, as I said a minute ago, at U naught equal to 6 in this case. Okay, but there are other possibilities, namely the similarity to quantum mechanics suggests that we can try to construct more actually maybe slightly more complex solutions, which in terms of quantum mechanics, which corresponds to m, which is smaller than L. And first we can try to construct a solution with when m is equal to 0, so we have no angular momentum, but still it will not be the ground state. It will not be the ground state because we still assume that we have the non-zero value of the orbital quantum number L, again, in terms of quantum mechanics. Then, if we have some threshold at which this solution appears, this solution with infinitely small amplitude should be naturally proportional to the standard spherical harmonic, capital Y, with a set of subscripts indices 1 and 0. L is equal to 1 and m is equal to 0. First we take the simplest possibility, L is equal to 1. Then it's easy to see that this solution, which is exact when the amplitude is infinitely small, is simply cosine of theta. This is a difference from previous solutions. The previous, what is called the previous sectoral solution, it had sine of theta, and in quantum mechanics, such a bound state when we have the angle, when we have non-zero orbital quantum number, but exactly zero magnetic quantum number, it's usually called the zonal state, zonal mode. So for the zonal mode, we have this approximation. This approximation is exact, infinitely close to the bifurcation point or threshold point. Now, the value of the threshold is predicted once again by this formula, this expression L times L plus 1. Now we have the value, the threshold value is 2, the same as we had before. Before we had the case of the sectoral state with both L and M were equal to 1. In that case, the threshold corresponded to 2. Now we have L equal to 1, M equal to 0, but because the threshold it depends only on L, does not depend on M, we still have the same threshold, U not equal to 2. And then we apply the same approximation, essentially the same approximation as before, namely, we take our approximate solution, substitute it into the cubic term, just we use essentially, formally speaking, the same trigonometric formula, where we, instead of sine, we have a similar formula with cosine. The formal difference is that here we will have cosine of theta and not minus but plus cosine of 3 theta. But in any case, we neglect the third harmonic, keep only the fundamental of first harmonic, collect all terms with this fundamental harmonic, and easily predict the amplitude of this zonal state solution at small values of U0 minus 2. It's written here, so again, it will be proportional to the square root. Okay, then we can consider another example, namely, as I said, generally we would like now to understand the structure of the solutions when we have non-zero value of L and the value of M is smaller than L. So now we can take the situation when L is equal to 2 and M is equal to 1. So both quantum numbers are different from 0. But L is larger than M. And usually in quantum mechanics, such a bound state is called a tesseral mode by tradition. Tesseral mode, a tesseral bound state, when M is smaller than L, but is not equal to 0. So the simplest possibility is to take L equal to M equal to 1. Then the threshold, according to the same general expression for the threshold, which does not depend on L, but on M, only on L. Now we will have L equal to 2, it means 6. The threshold value will be 6. And the structure of the wave function now for this tesseral mode, it will be the structure is written not here, so I'm sorry, not here, it's written here, yes. The natural structure is essentially the same as a standard spherical harmonic Y with the indices to 1, namely it's sine of 2 theta. Sine of 2 theta. And now again we assume that we have a small amplitude. It's infinitely small exactly at the threshold point when U0 is exactly equal to 6. And when U0 is slightly larger than 6, we assume that we will have such a non-zero small amplitude, and this will be the result of this approximation for the squared value of this amplitude. Okay. Still another example, we can again keep L is equal to 2, but now take M equal to 0. So this will be what is called the zonal state, but with a higher value of L. Previously, we only considered L equal to 1. Now we can also consider the zonal state with L equal to 2. In a sense, it will be the shape of the solution will be a sandwich-shaped form, because if we look at the alternation of signs of the wave function, it will be like minus plus minus. In that sense, it's like a sandwich. Okay, anyway, the analytical form of the solution is determined by the commonly known expression for the spherical harmonic Y with indices 2 and 0. So this will be this expression 1 minus 3 cosine squared of theta is a standard form of this spherical harmonic of the of the zonal spherical harmonic. And we once again assume that we have a small amplitude here. The amplitude is infinitely small, exactly at the threshold. Threshold, because it's determined by L, will be the same. L equal U0 equal to 6, as we discussed it. And then we will obtain the final result. Actually, the expression for the amplitude the expression for the amplitude will be actually not explicitly written here for this V naught, but it will be essentially the same as here. Okay, then there is still another possibility to produce an approximate analytical solution. It's completely different possibility. So let us recall what we did. We looked at this ordinary differential equation, which in the limit of r going to 0 determines this equation. This equation determines the angular structure of the bound state with non-zero angular momentum when the asymptotic form of the wave function when r is approaching 0. Okay, and we tried to construct approximate solutions when we assume that we are close to each particular threshold at which a new solution appears. Now, another approximation is possible when we do not consider the case when U naught is close to some threshold value. Instead of this, we simply say, let us look at the possibility when U naught is very large. When U naught is a very large parameter, we can assume a different analytical approximation, which is called the Thomas-Fermi approximation. The Thomas-Fermi approximation is the approximation which simply assumes that this U naught is a large parameter, and then in the lowest approximation, most primitive approximation, we can completely neglect terms with any derivative with respect to theta. So we replace this ordinary differential equation by the simple algebraic equation. Of course, this solution is immediately obvious. There may be two solutions. Either V is simply equal to 0, or we have a non-zero solution given by the square root. Let us look at it. So it's written here, yeah. So it's actually this Thomas-Fermi approximation is written for the squared solution. So according to this remaining algebraic equation, we immediately have this simple expression for the solution if it is positive, because of course square is relevant only if it gives us a positive expression for the square. If formally it gives us the negative expression for the square, it's known that we should simply take V equal to 0, because V equal to 0, formally speaking, is also a possible solution in the Thomas-Fermi approximation. So this is a standard form. So as is in any case, when we apply the Thomas-Fermi approximation, the solution itself is continuous, but its derivatives with respect to theta, they make a jump at the point where we have the boundary between this non-zero and zero parts of the solution. So this is a rather typical example of the Thomas-Fermi approximation. Okay, and then in particular, what is a characteristic feature of this Thomas-Fermi approximation? A characteristic feature is if we look at this expression for this simple expression, we can try to identify its largest value. And the largest value corresponds obviously to the situation when sine of theta takes also largest value in the denominator when it's equal to 1. So the largest value of the squared solution is given by this simple expression, 1/2 U naught minus m squared. As a matter of fact, the applicability of the Thomas-Fermi approximation is that U naught should be definitely larger than m squared, otherwise it does not make sense. And moreover, U naught must be simply a large parameter. M may be not very large, or it may be large, and so that m squared will be close to U naught. In either case, the Thomas-Fermi approximation is applicable if U naught is a large parameter. So m may be anything, any integer, which satisfies the condition that this expression must be positive. And by the way, there is a more general possibility. We can apply. So we applied here the Thomas-Fermi approximation. We applied the Thomas-Fermi approximation to our equation, which we had here. This is the equation for the angular part of the wave function at small values of r. But we derived this limit form of the equation from the three-dimensional equation. The full three-dimensional equation was written here, and then we arrived at our ordinary differential equation, just setting that r is equal to 0. Now we can look at the full three-dimensional form of this equation, not only at r equal to 0, but at all values of r. And here too, we can apply the Thomas Fermi approximation. I mean, in this equation as well, we can, at non-zero values of r, we can drop the derivatives, which means we will drop three terms. This one will be dropped, this one and this one, but there remains now a new term. When r is different from 0, we have the extra term, which will make its contribution to the three-dimensional version of the Thomas Fermi approximation, and it means we will arrive at some expression, which we will not discuss in detail, but just to mention this possibility. The possibility is that we can construct, if we want, also this slightly more sophisticated result, which produces the Thomas Fermi approximation for the full three-dimensional wave function. Okay, so this were some analytical predictions for the solutions of the bound states, which give us the bound state of this, as a matter of fact, Bose-Einstein condensate in the singular attractive potential, and we consider the states which carry non-zero angular momentum. Now, what we can do, we can produce a numerical solution of the same full three-dimensional equation. Let us again look at it just to be sure what we are talking about. So this is our original equation. As a matter of fact, now we're talking about the stationary equation. So the stationary equation is explicitly written here, or after we separated the singular and non-singular, after we separated the singular, and so this is the full three-dimensional equation, and after we separated stationary equation, after we separated the singular factor and remaining non-singular factor, eventually we would have to solve this partial differential equation for v, non-singular radial part of the wave function, as a function of radial coordinate and angular coordinate theta. Now all this can be done numerically. We can produce such solutions, and we can also compare them to these analytical predictions which we discussed. Okay, so let's look at some results. First of all, we can do it for the simplest bound state of what is called sectoral, it's a state bound state of the sectoral type in quantum mechanics. So once again, this is a set of of quantum numbers where both L and M are equal to 1. So this is, first of all, the radial structure of the solution, V as a function of R. It's shown, because V is also a function of theta, is shown as theta equal to pi over 2 when as a function of the angular variable, it attains a maximum. So this is a maximum value of the wave function as a function of the radial variable. And the dashed curve is actually not a real analytical approximation. It's simply the fit of this numerically found solution to the exponentially decaying, asymptotically decaying analytical expression. Okay. Now we can take a solution that R is a limit of R equal to 0, because this is exactly what we analyzed by means of the analytical approach. And now we can look at this numerically found solution. So now let me remind again, mathematically speaking, what we would like to solve in this limit of R equal to 0. In this limit of R equal to 0, we had this equation, and then we discussed approximate solutions that we could obtain analytically, but we can also solve it numerically. Now we can compare analytical and numerical solutions, and as currently we are doing this for the so-called sectoral state when both L and M are exactly equal to 1. Okay, so this is a solution as a function of theta. Theta obviously takes values between 0 and pi. And now we see the continuous curve is a numerical solution, and almost identical to it is the dashed curve, which is an analytical approximation. They're almost identical. And actually, this particular example is shown for u not equal to 2.5. Let me remind that the threshold value for this solution is u not equal to 2. And the analytical solution should be applicable if u not minus 2 is a small parameter. Currently, for this example, u not minus 2 is 0.5. 0.5 is not a very small parameter. And nevertheless, for this not very small parameter, we see that the analytical approximation is very accurate. Okay, and this is some other characteristics for the same solutions when L and M are both equal to 1, this sectoral type of the solution, right? Now this is, now we characterize here the entire family of solutions. Entire family, I mean solutions obtained for different values of u naught, of the strength of pull to the center. So we see that exactly as predicted, the family appears at the threshold value u not equal to 2. When u not is smaller than 2, we don't have solutions, they don't exist. And then we have this is actually, as a matter of fact, v as a function of at the pi over 2. This is at r equal to 0. This is the largest value of the solution. The maximum value of the wave function at r equal to 0, of this non-singular part of the wave function, of course. So we see this continuous, not continuous is better to say, the dashed curve is a prediction of our analytical approximation, and simultaneously a set of rhombuses, these are numerically found solutions. So we see that even when u naught becomes as large as 4, still the analytical solution is rather close to its numerical counterpart. And let me remind once again that the condition for the applicability of the analytical solution was that u naught minus 2 had to be a small parameter. At this point, u naught minus 2 is 2. 2 is definitely not a small parameter. So formally speaking, we are quite far from the applicability of the analytical solution. Nevertheless, the analytical solution still gives a rather accurate prediction in this case. On the other hand, what is shown here, this is an example when we want to consider very large value of u naught, it's u naught equal to 20. So let's say here's the largest value of u naught equal to 4. Here is a much larger value, 20, because here we would like to test the applicability of the Thomas Fermi approximation, which is valid for u naught equal to 20. And in this particular example, what we see, this is the dashed curve, shows the Thomas Fermi approximation. It has this characteristic property. We have this point outside of this region. The Thomas Fermi approximation simply gives 0. And at this point, between these points, we have the non-zero prediction for the wave function. And the full analytical solution, the full numerical solution, which is produced in the same case, is shown by the continuous curve. So we see, of course, definitely in the periphery, when formally speaking, Thomas Fermi predicts 0 solution, is definitely the exact solution is different from 0. But overall, the structure predicted by the Thomas Fermi approximation is reasonable, and moreover, the maximum point here, the amplitude of the solution, is predicted practically exactly. Okay. Now this is another example. Again, we take the solution of the same zonal, sectoral type. Sectoral type is by definition when L and M are equal, but now we take, instead of L and M equal to 1, we take an example when L and M are equal to 2. So here, what is shown here, this is something, plots, they show something similar to what we discussed a minute ago. So here we discussed it actually for, we can look, so in this plot, we discussed the comparison between the analytical and numerical solution at some value of u naught. And here we discuss the dependence of the maximum value of the solution as a function of U0 for the entire family. Now we have similar results, but now when L and M not equal to 1, but both are equal to 2. So first of all, this is a particular example of the solution, and this one is taken for 6.5. What it means, in this case, the threshold value is 6, and the applicability condition is, as usual, U0 minus the threshold value should be smaller than 1. Here, this parameter is 0.5, 6.5 minus 6.5. It's not very small, but it gives a practically exact approximation, as we see. There is virtually no difference between the analytical solution and the numerically found counterpart. And here, this is a characteristic of the family. So we start from the threshold value, which is 6, gradually increase U0, and we can, here this dashed curve is a prediction of the analytical solution, and the chain of rhombuses again numerical solution. So now we see that in comparison with the previous case, the discrepancy is a little bit larger, but still, even up to U0 equal to 8, what it means. When U0 is equal to 8, U0 minus threshold minus 6 will be 2. 2 definitely is not a small parameter, it's quite large. But nevertheless, we see that the analytical prediction, which formally relied upon the conditions that U0 minus threshold was small, even in this case, the analytical prediction is reasonable. It's not very accurate, but it still remains reasonable. Now, these are some other examples. This is examples for the bound state of the zonal type. Let me remind, zonal, this means we take the simplest case. L is different from 0, L is equal to 1, but the magnetic quantum number is 0. Okay, so this is a typical structure of the solution at r equal to 0 as a function of the angular variable theta between 0 and pi. So the continuous curve is the prediction of the analytical approximation. The dashed curve is a prediction of the analytical approximation. The continuous curve is a numerical solution. And here the value of U0 is 4. And here, in this case, the threshold value was 2. So the analytical solution is formally applicable when U0 minus 2 should be a small parameter. Currently, U0 is 4, U0 minus 2 is 2. U0 is, so this value 2 is definitely not a small parameter. So the analytical approximation indeed shows some discrepancy in comparison with the variation with the numerical counterpart. Nevertheless, they are still more or less close to each other. So in this case, when formally speaking, the analytical approximation should have no validity, it still produces a rather reasonable result. And this is just a purely numerical characteristic. This is a structure, the radial structure of the solution. V is a function of r. It's taken at theta at point theta equal to 0, because for this zonal state, the maximum of the solution is attained not at theta equal to pi over 2. This was the case for the previous, the sectoral state. For the zonal state, the maximum is attained at theta equal to 0. Okay, and then this is again the characteristic at r equal to 0. This is the amplitude of the solution. Again, it starts now for L equal to 1, the threshold value is 2. Starting from 2, we have the family of such solutions as we gradually increase U0. The dashed curve is the prediction of the analytical solution, and the chain of rhombuses are numerically found solutions, and up to U0 equal to 4 when U0 minus 2 is 2. So this is no longer a small parameter. Still, the analytical approximation is relatively accurate. And still another example. This is what traditionally is called the tesseral type of the bound state, when both L and M are different from 0, but their also different from each other. So M is 1 and L is 2. Okay, so this is the case when, in this case, the threshold value is 6, and this solution is shown for U not equal to 8. So 8 minus 6 is 2. It means that the distance from the threshold, from the bifurcation point, is not small. It's equal to 2. Nevertheless, here the comparison of the numerical and analytical solutions demonstrates that they are still, even for this relatively large deviation from the threshold, practically the analytical approximation gives us the exact solution. We cannot distinguish between them. This is the radial structure, is purely numerical solution. And again, this is a characteristic of the family of solutions. The maximum value is shown as a function of U naught, starting from the threshold point from 6. This is again the family of analytically predicted solutions and a set of numerical counterparts. And see that even up to U not equal to when this what should be formally a small parameter is 2, it's no longer small. Still, the analytical approximation is quite accurate. Okay, so it means that we have completed all this large topic. We can complete all this large topic of bounce and condensate, attractive singular potential. Now we can summarize the main points of this analysis. So this is attempt to resolve the well-known problem of the quantum collapse, or the so-called fall onto the center, which is induced by the singular attractive potential of this type minus U naught divided by square of R in 3 and 2-dimensional geometries. So first of all, it was found that if we now replace the linear Schrödinger equation by the Gross-Petayevsky equation with a self-repulsive term, usual cubic self-repulsive term, then we remove the singularity, we completely suppress the quantum collapse, and we obtain a well-defined ground state. In 2 dimensions, the cubic nonlinearity is not sufficiently strong to do it. And in 2 dimensions, if we want to suppress the collapse, which is stronger in that case, we need to consider the physical system which allows us to have a stronger nonlinearity, which means more formally it's a quintic nonlinearity, or more relevant in terms of physical realizations, it may be the quartic additional nonlinear self-repulsive nonlinear term, which is produced by the quantum corrections to the mean field theory. So we could produce an estimate for typical physical characteristics of such newly created ground state in 3D. It was for typical parameters. It was predicted that its size, radius, would be measured, would be on the scale of several microns. And also the analysis was extended, and it could produce not only the well-defined ground states trapped in this singular potential, but also the bound states, high bound states with non-zero angular momentum. Okay. Then we considered also some approximations, particularly in 3 dimensions. We considered a different geometry when the symmetry was reduced from spherical to cylindrical. Namely, we assumed the situation when we had a strong external, so the physical interpretation of this model is that we may have a 3-dimensional gas of molecules, small molecules, which carry a permanent magnetic moment. Excuse me, of course, permanent electric dipole moment, and they were attracted to the center because at the center we simply placed an electric charge. So this was the attraction of the electric dipole moments to the charge. Now, what we also considered was a different geometry with a reduced symmetry, when instead of we additionally introduced the strong DC polarizing electric field imposed on all the system. It means that at each point, the vector of the dipole moment was not did not point at the center, but it simply kept the fixed polarization, fixed direction along a fixed coordinate, which was imposed by this strong polarizing field. In that case, the analysis was more involved, but nevertheless, the prediction was that still we suppress the cubic nonlinearity in 3D is sufficient to suppress the collapse and predict the well-defined bound state. Also, it was briefly mentioned that we may extend this prediction for the binary gas when we have a system of such two coupled Gross-Petaevsky equations. Also, I mentioned briefly that these predictions of the mean field theory were compared with the analysis based on the many body quantum theory, and the conclusion of the analysis was that, strictly speaking, what the mean field predicts as a ground state, strictly speaking, it still is not a ground state, is a metastable state, but it's separated from the collapse, because the collapse cannot, in the framework of the many body quantum theory, collapse cannot be completely suppressed. However, this state which was predicted instead of the collapse by the mean field, it also appears in the framework of the many body quantum theory, but it appears as a metastable state which is separated from the collapsing one by a sufficiently tall potential barrier, and eventually, if roughly speaking the number of particles becomes on the order of 100 or larger, this potential barrier is so tall that practically it becomes impenetrable, and it means that, practically speaking, indeed, what we can predict may be considered as a ground state. Okay, so this is all that. Still one more. Okay, but this is what I already very briefly mentioned. Let me say again, as concerns the two-dimensional configuration, I mentioned already now that the usual cubic nonlinearity, mean field nonlinearity, is not strong enough to suppress the two-dimensional quantum collapse, and the most relevant possibility is to consider the stabilizing effect of the Li-Huang-Yang effect correction produced by the quantum fluctuations of the mean field theory, and they predict the singular state when the density singularity at small values of r has this form r to the power minus 4/3. Nevertheless, this singularity is weak enough to allow the norm integral to converge, and therefore we still have a physically relevant prediction for the suppression of the quantum collapse and the replacement of the quantum collapse by the physically acceptable ground state. Okay, so thank you for your interest in this part of the lecture, and this is a possibility to request copies of the presentation of some articles. And now we still have an hour today, a little bit less than an hour, and let us at least briefly consider the last topic. Maybe if we will have a chance to continue such lectures in another semester, we will consider it in more detail, but at least today we can consider this topic. This topic will be, roughly speaking, systems of linearly coupled Ginzburg-Landau equations. So now we will consider, unlike what we did in previous lectures, now we will consider a class of models which are essentially dissipative, which represent nonlinear dissipative systems. Okay, so it's very well known and was already explicitly mentioned more than once in earlier lectures that the simplest model for the nonlinear dissipative system is provided by what is called the complex Ginzburg-Landau equation. So the simplest possibility is written here. It's roughly speaking like the cubic nonlinear Schrodinger equation, but with the difference that the coefficients in front of the dispersion term here and the cubic term here are complex. So the imaginary, in this notation, the imaginary parts of these coefficients, they reproduce here, they reproduce the so-called filtering, and here it reproduces this term gamma 2, which is positive, reproduces the nonlinear loss. Literally in this form, this is a model for the dynamical model for the evolution of the amplitude of light in the fiber laser. Therefore, it's written in the optical notation, where the evolutional variable is not time, it's z is the propagation distance, and the formal coordinate, it's actually, physically speaking, the temporal variable in the optical fiber, the so-called reduced time. And now, if we have actually these two terms, gamma 1 and gamma 2, if they are positive, they represent losses. Here, these are dispersive losses, here nonlinear losses. To have something non-trivial, we must also have, of course, the gain. And gain is represented by this linear term, and so gamma naught is positive. So this is a typical situation in the laser, for example, when we have the gain provided by the lasik mechanism, and it competes with nonlinear losses. Nonlinear losses, it will be, physically speaking, the two-photon absorption in the material of this fiber. And also we have some spectral structure of the gain, and the fact is that we have some particular wavelengths at which we have the maximum of the gain, and if we change the wavelengths, we will have actually the decrease of the gain. It is represented by this loss term, which represents what is called the spectral filtering. Okay, so then there is a simple mathematical fact, which was first found in terms of when this equation was used as not in optics, but as a phenomenological model in hydrodynamics, actually, the phenomenological model for the nonlinear flow of viscous fluid in a pipe. This is actually what is called in classical hydrodynamics the Poiseuille flow. So it's known that the Ginzburg-Landau equation may be used as a phenomenological model for the unstable Poiseuille flow, in particular for the description of turbulence in the Poiseuille flow. And in this context, for the first time, by Hawking and Stewardson, it was demonstrated that this equation has an exact mathematical solution, which formally speaking is a soliton. It's localized, roughly speaking, similar to the soliton of the nonlinear Schrodinger equation, and the formal difference from the soliton is that in the classical soliton it will be simply hyperbolic cosine. Now it is hyperbolic cosine which is raised to power which has the imaginary part mu. So mu in terms of optics, mu represents the so-called chirp. Chirp means that if we look at this is a complex expression, we can look at its phase, and phase will be now a non-trivial function of tau. This is more or less what is called chirp in optics. So the same solution was found a little bit later by Pereira and Stanford, also not in terms of optics. They used this Ginzburg-Landau equation, actually some model of the instability development in plasma physics. They found the same exact solution. So it's a nice solution, which is similar to a soliton. However, there is a serious problem about the solution. Soliton solutions of the nonlinear Schrodinger equations are completely stable. This solution is obviously unstable, and its stability is completely obvious. Why it's obvious? It's a localized solution. So if we try to look at the evolution far from its center, it vanishes, it becomes equal to 0, and then if it becomes the asymptotic tail of the solution is 0, their nonlinearity may be neglected, and then we see that we have immediately the action of the gain. So if we consider any arbitrary small perturbation far from the center of this dissipative soliton, we see that the perturbation will be actually driven by this gain. As a small arbitrary small perturbation will start to grow exponentially, which means that we do have this formal localized dissipative soliton, but it's completely unstable because it sits on top of the zero background, and the zero background is trivially unstable in the framework of this Ginzburg-Landau equation against growth of any arbitrary small perturbation. Okay, so the simplest possibility to stabilize this non-linear instability, so it's necessary to try to introduce a more sophisticated version of the complex Ginzburg-Landau equation, in which it will be possible, it will be interesting to have stable dissipative solitons, and phenomenologically, not in direct relation to any physical model, but just from the general principles, it was predicted, this possibility was proposed very long ago in Russia by Petveashvili and Sergeyev. This is the original paper where they produced this possibility, and the possibility is to have this equation. So this in this case, what happens? First of all, parameter gamma, this term linear gain gamma naught is still formally written with positive gamma naught, but it's written on the other side of the equation, on the left-hand side. Therefore, now it's not gain, it's loss. So it means that the trivial solution u equal to 0 will be trivially stable, as a matter of fact. And for this reason, at least, we may have a chance to produce something which will be localized and stable. Next, we still have this spectral filtering as before, but we need, of course, to have some gain. We need to have some gain if we want to produce not only zero solution, but something non-zero. So previously, we had the cubic term in the previous form of the Ginzburg-Landau equation, right? And this cubic term, it represented nonlinear losses. So the proposal of Petveashvili and Sergeyev was to write this term so that this coefficient gamma 2, in comparison with the previous, its counterpart in the previous equation, is positive. If we would write it in the same position on the left-hand side, as it was written before, it would be negative, which means that now it represents not cubic loss, it produces a cubic gain. However, if we only have this term, so we will have the competition between linear losses and cubic gain, and of course, because for strongly nonlinear perturbations, the cubic gain would be stronger, it means that the situation would be catastrophic, the system would blow up under the unlimited action of this cubic gain. So the main idea of Petveashvili and Sergeyev was to phenomenologically propose the higher order quintic fifth order term. Here I'm terribly sorry because I didn't see that here there is a trivial and stupid typo, because this quartic factor should not appear here. It appears only here. I'm sorry. So you can ignore this. So it was simply written twice due to negligence. I'm sorry. So here there is no such. This is only coefficient g without this factor. Okay. So in any case, this coefficient gamma 4 is also positive. And now gamma 4 is easy to see. It gives rise to higher order quintic loss, which this quintic loss would compete with the cubic gain, and therefore it would arrest the blow up. It will not allow the system to develop very large values of the amplitude. And therefore, so here essentially we have what is called the cubic quintic complex Ginzburg-Landau equation. And overall, we have the following competition. We have the competition of the cubic gain with two dissipative terms. We have two types of dissipative terms. We have linear dissipation or linear loss, and also we have the quintic loss. And there is a chance that maybe due to the competition between, as a balance between all these terms, we will be able to predict self-trapped, localized dissipative solitons, and this time maybe it will have a chance to be stable. So actually, for the first time long ago, the ability of having such a stable dissipative soliton is predicted in this paper back in 1987. As a matter of fact, what happens is that if we want to have a chance to predict a stable dissipative soliton, it's necessary to predict simultaneously two solitons. For what reason? One will be stable, one unstable. So just a stable soliton cannot exist. It may only exist having as a companion an additional unstable soliton. The reason is that this is a dissipative system. In the dissipative system, if we have a stable solution, the stable solution is what is called an attractor. Attractor will we can take a more or less arbitrary initial condition, and due to the nonlinear dissipative evolution, it will be attracted gradually to a stable stationary solution. So in any case, because we want to have this dissipative soliton, it means automatically that the background of the soliton is stable. We discussed. We will have a trivial attractor, just a zero solution. Of course, it's trivial, but still it's an attractor. And then we want to have a situation when the attractor, a stable dissipative soliton. So this means that we can now try to analyze what initial conditions will be attracted to each of the two coexisting attractors, one trivial, one non-trivial. In other words, we can try to define what is called the basin of attraction, the set of initial conditions which are eventually attracted either towards the zero solution, so they trivially decay to zero, or they will instead form a non-trivial, stable, dissipative soliton. Now, if we have two basins of attraction towards these two coexisting attractors, we necessarily must have some boundary between the attraction basins of the two competing attractors. There should be a stationary solution. So eventually, this stationary solution boundary separating the attraction itself is a soliton, a stationary soliton, but of course, it is definitely, by definition, it's unstable, because if we apply a small perturbation, then the evolution will be pushed either towards the zero solution, the soliton, this unstable soliton will start to decay, or towards the non-trivial attractor, which means that this unstable dissipative solitons will spontaneously start to rearrange itself into its stable counterpart. So the conclusion is we may have a chance to find a stable dissipative soliton, but only if we will find it together with its unstable companion. Okay, so this is how we can predict the possibility to have stable dissipative solitons. Now, there is another type of the generalized Ginzburg-Landau equation where it's possible to predict also stable dissipative solitons still without adding the quintic nonlinearity. It's possible to have another type of the model in which nonlinearity remains strictly cubic, and nevertheless, stable dissipative solitons will become possible. And this was proposed also quite some time ago in this paper. Now the idea is to replace a single Ginzburg-Landau equation by a coupled system of two Ginzburg-Landau equations. So they're written here. So now we have a coupled system of equations for two complex amplitudes u and v. Now, what we assume, first of all, as concerns the coupling. Coupling is represented by this real coefficient kappa, which means that we have the linear coupling between them, and it's enough to assume that there is no nonlinear interaction. Of course, we can also introduce the nonlinear interaction, but it's not necessary. It's enough to have just these two almost isolated cubic complex Ginzburg-Landau equations, just with the linear coupling between them. In optics, it can be quite easily realized because we can consider a fiber laser, which is based on the dual core fiber. So we can assume that the gain, the lasing effect, is applied only to a single fiber, to a single core, and the parallel core is purely lossy, purely dissipative, without any gain. Well, experimentally, it can be realized as a matter of fact. This system with two cores may be symmetric, and the cores, as a matter of fact, may be identical, but the external pump, which gives rise to the lasing, to the gain, can be applied only to one core, and the other core is kept dark. It's not pumped by the external source of light, and therefore it remains purely lossy, purely dissipative. Okay, then we will have this system of two equations, and now, according to what I said, we assume in the first equation we have this positive parameter gamma naught, and if you compare these two terms, you can immediately conclude this is nothing else but exactly the linear gain. Then, as in the previously introduced equation, we should have also a cubic loss, and we should have also the dissipative loss. Here, as a matter of fact, it's enough to consider the simplified version when we only, by this parameter gamma 1, introduces the dissipative loss, or what's called spectral filtering. And as concerns the cubic terms, it's enough to keep the cubic part completely conservative. In terms of optics, it represents just the kernel linearity, and it's not necessary to explicitly introduce nonlinear loss, that is a two-photon absorption. And then, roughly speaking, the same we assume about the second component for the second core. So we have, this is, by the way, this is a standard term which represents the group velocity dispersion. In this form, it represents the anomalous group velocity dispersion, because we would like to construct a soliton. Of course, for the soliton, we need to have the anomalous group velocity dispersion. It's an elementary effect. So these two terms in combination, if they are part of the nonlinear Schrödinger equation, they will immediately construct a family of solitons. Now, they will be replaced by some dissipative solitons, and the most important problem is how to make this dissipative soliton stable. So now we assume that, as concerns the linear gain, as I said in the first core, we postulate that we have the linear gain with strength small gamma naught. In the parallel core, we assume that we have only losses, linear losses, with the loss parameter capital gamma naught. As a matter of fact, as we will see, it's necessary to assume that this loss in the passive core or the dissipative core must be stronger, larger than the gain in the active in the active core, which carries the gain. So this can be a model of the dual core fiber laser. Also, it may be realized in optics as a model of a planar waveguide. So it may be the laser based on the planar waveguide in the spatial domain. In that case, the evolution variable remains the propagation distance. And this variable will not be the temporal variable, it will be simply the transverse coordinate. And these two terms will simply represent the paraxial diffraction. Okay, so as I said already, we will see from the detailed analysis that this system of two coupled equations, it works as follows. Why it may have a chance to produce eventually stable dissipative soliton. Of course, if we look just at the first equation, we see that we have this familiar problem. We have, far from the center of the soliton, practically we have zero solution. And on top of the zero solution, we may have a small perturbation, and this linear gain will drive the exponential growth of the small perturbation. Now, what is new in this case? We have the linear coupling from this core to the parallel core. This linear coupling may have a chance to transfer this growing perturbation from this active core into this parallel passive core. And once it is transferred by the linear coupling, here it will be quickly killed by this stronger linear dissipation, linear loss. And so if we have this interplay of the linear gain in the first core, a stronger linear loss in the second core, and the linear coupling between them, the transfer of the perturbations between them, the interplay of this factor is sufficient, as it can be easily checked, to provide effectively the stability of the zero solution. The small perturbation will not be growing. And if it will not be growing, maybe we will have a chance to have a stable soliton with a zero background. Okay, so there is actually some review paper, if you are interested, relatively old review papers on this type of the models. Okay, so let's proceed. Okay, so first of all, it's possible to make some analytical predictions for the first time. And then it was also, I mentioned already that analytically this possibility was predicted in this paper, and then it was for the first time numerically verified in the companion paper here. Okay, so let us look. So this is once again our system of two coupled Ginzburg-Landau equation. Actually here the system is taken in a slightly different form, but essentially it's the same principle. So now here for generality, so to say, we also have coefficient gamma 2, which means that we include, if we want, we can include the cubic loss to photon absorption in the active core. In the previous form of the model, it was not included. It can be included. It's not a dramatic difference. Now the coupling, linear coupling, is reproduced by these terms V and U. This coupling coefficient, it previously was called kappa. Now by scaling, it's set equal to B1. Now we have familiar terms. This capital gamma naught is the loss in the passive core, and small gamma naught, which is positive in this notation, is the linear gain in the active core. Gamma 1 is the familiar coefficient of the dispersive losses, or what's called spectral filtering in the active core. We need to have it. Sigma is just, once again, the Kerr coefficient of the it's a conservative nonlinear term as before. And then as concerns the structure of the equation for the passive or dissipative core, here nonlinearity is neglected. Why is neglected? Because we will have solutions in which actually the component of the solution in the second core will be small. Therefore, the nonlinearity may be neglected. Also, we may neglect the presence of the filtering of the dispersive losses in the second core, simply because it's not necessary for the stabilization of the soliton. So to isolate the most basic model, we can neglect the action of the spectral filtering in the lossy core. So in the lossy core, essentially, we must have two terms. We must have its linear coupling to the active core, and we must have its own sufficiently strong, but not extremely strong, we will see it, linear loss. By the way, we can, if we want, we can also have this parameter k naught. K naught means it's not absolutely necessary to have it, but we can introduce it. It would mean that we have some mismatch between the in terms of optics, mismatch between the propagation constants in the two cores. It may be also included. Okay. Now what we can do? We can here there is an interesting possibility. I mentioned that long ago it was found that if we have just a single cubic complex Ginzburg-Landau equation, this one, it was found long ago that it's possible to have an particularly exact analytical solution in the form of the dissipative soliton. Also, it was not physically relevant solution because it was completely unstable. But as a formal solution, it was available. And now there is a pretty simple possibility. Let us try to find the exact analytical solution of the same type. Also, roughly speaking, using the ansatz where we have the hyperbolic cosine is the denominator, raised to the power 1 plus I times imaginary part, some chirp, and let us check if we will have a chance to find such an exact two-component soliton solution in our newly introduced system of two linearly coupled Ginzburg-Landau equations. Okay, so this means what is written here. Two components of the soliton are looked for in this form. So capital A and B are two amplitudes. We have this hyperbolic secant, right? K is just the propagation constant of the solution. We have hyperbolic secant, chi determines the temporal width of this soliton. And then we have the power 1 plus I times mu. Mu is a Chern parameter. And the answer is yes. If you substitute these answers into our system of two linearly coupled Ginzburg-Landau equations exactly in this form. Actually, this is why it was here, for instance, the cubic term and the spectral filtering were dropped from the second equation, not only because they are not really necessary, but also in that case, it's easier to analyze this exact solution. Okay, so the result will be, first, this coefficient mu, which is an interesting parameter, of course, because it determines the chirp, the phase chirp of the soliton, is given by this rather complex but nevertheless explicit solution. Then we have the exact expressions for these amplitudes A and B. So this is the square of A, and this is B. So B is actually the amplitude in the lossy core, and A is the amplitude in the active core with the gain. Then we have the parameter chi. Chi is determines the temporal width of the soliton. We have this exact expression for it. Here, by the way, this is actually, in a sense, this is a simplified expression. It's written when we can still neglect also the gamma 2. So we can, it's not absolutely necessary to include the filtering the active core. And then we can include it, and this dissipative soliton will exist, but we can still have it even when we set gamma 2 is equal to 0. Then it will be slightly less cumbersome to write the solution. So this is the expression for chi, or chi squared. Of course, the condition is that chi squared must be positive for the relevant solution, and eventually there remains to determine the value of the propagation constant k of this soliton, and it is determined eventually as a part of this exact solution by this cubic equation for k, which is, of course, includes other parameters, and so this cubic equation should be solved. A principle, as we understand, because this is a cubic algebraic equation with real coefficients, it may, and of course, the physically relevant solution must be real. We may have either one or three of three real solutions. Okay. Now we can further to simplify the solution. It's still possible to set k not equal to 0. K not, I said that for the generality we introduce this as a mismatch, but we can still neglect the mismatch in order to have this analytical solution as simple as possible. And eventually we will have a set of two fundamental and very simple solutions which provide for the existence of the exact soliton solution of this type, and moreover then we can identify parameter regions in which it will be stable. But first of all, the existence. So in this more simple form, when we neglected k naught, eventually we have two very simple conditions, physically clear conditions, which are necessary to provide the existence of this solution. First of all, small gamma naught is smaller than capital gamma naught. I said already what it means. It means the linear gain in the active core must be smaller than the linear loss in the parallel gain, which means that the linear loss in the passive core will be strong enough in order to be able to suppress the perturbations. Simultaneously, we have the second necessary condition: the product of these two coefficients, gain and loss together, must be smaller than 1. What is 1? 1 is actually if we write it in the more general notation, we will have kappa. Kappa was the coefficient of the linear coupling. Now it's simply normalized to be equal to 1. So the meaning of this condition is also quite simple. The product of the linear gain in the active core and the linear loss in the passive core, the product of them should be smaller than the square of the coupling coefficient between the two cores. And it means that actually, it simply means the coupling should be strong enough to be able to pick up growing perturbation from the active core, transfer it into the passive core, and then let linear loss in the passive core suppress this perturbation. Now, the solution becomes really simple if we additionally consider the situation when this condition is satisfied, but we are close to the threshold, which means the squared coupling coefficient is only slightly larger than the product of the gain and loss parameters. So in that case, we have actually these relatively simple expressions. And finally, we have one more condition for the existence of this. So we had two very simple conditions for the existence of the soliton, and now we have the third condition, also some condition imposed on parameters, which includes essentially gamma 1. Gamma 1 is, let us remind what gamma 1 is. Gamma 1 is the coefficient of the dispersive losses, spectral filtering is the first equation. Okay, and then it appears here, and we have finally this condition, and this condition together with two previous ones, this one, and finally this condition, it will provide, together this set of three conditions will secure the existence of exact dissipative soliton solutions of this system of two linearly coupled Ginzburg-Landau equations. Of course, the solution is still rather cumbersome, but nevertheless, in principle, it's an exact analytical solution. Okay, then what is quite important is to analyze the stability of this condition, of this solution. So as I said, in the old form, when it was known in the single cubic Ginzburg-Landau equation, the solution was actually useless. It could not be physically relevant one because it was unstable. And now we can actually these simple conditions that we introduced here, simple conditions together. This one and this solution together, they provide automatically the stability of the zero solution against small perturbations in this coupled system. Therefore, that obvious reason for the instability, which did not allow us to use the soliton in the single equation, the instability of the zero background now is removed. The zero background is stable. But still, it's not enough, of course, to claim the full stability of the dissipative soliton. It's necessary to check its stability in the full form against all kinds of perturbations. This should be done numerically, analytically. The form of the soliton can be found analytically, but we cannot analytically solve the stability problem. It should be done numerically. And this essentially, then we can fix some other parameters and vary two most essential ones. Gamma naught is the strength of the linear gain in the active core. Obviously, if we're talking about the fiber laser, it will be immediately controlled by the intensity of the pump light, which drives the operation of this laser. And simultaneously, we vary parameter gamma 1 And let me remind, gamma 1 is another necessary ingredient, is the coefficient of the dispersive losses, in other words, the coefficient of the spectral filtering. So if we fix all other parameters and vary these two ones in the plane of these parameters, in this finite area, we will have complete stability of the exact dissipative soliton. So this is a remarkable result. We will have a model, two coupled, linearly coupled system of cubic Ginzburg-Landau equations. This system admits the existence of a stable dissipative soliton. By the way, I mentioned that the stable dissipative soliton may only be stable if it exists together with a companion unstable dissipative soliton. In this case, when we have this exact solution for the stable soliton, we also have an exact solution for the unstable soliton. Why this is possible? Because I mentioned that one of the ingredients of this analysis was the cubic equation for K, and this cubic equation for K may have three different solutions, and actually two of them will correspond actually to a stable dissipative soliton and simultaneously to the unstable dissipative soliton. Okay, so once again, this is a stability region for this dissipative solitons in the parameter plane gamma naught and gamma 1. Actually, what is also essential, we had parameter sigma. Sigma is simply plus or minus 1. Sigma is here. Let us look at it again. Sigma is here. It is simply essentially the sign of the nonlinearity. If sigma is plus 1, it's the usual self-focusing nonlinearity, it's the usual Kerr nonlinearity. If sigma is minus 1, it's a more exotic case, but still possible in optics, when we have a self-defocusing nonlinearity, so to say, anti-Kerr. And so this, we know that when we have the classical nonlinear Schrodinger equation, solitons exist only for sigma equal to plus 1, which means only for self-focusing, if the group velocity dispersion is anomalous. Now, in this dissipative model, what is interesting, exact one-dimensional, exact dissipative solitons exist even for the case of the self-defocusing nonlinearity. Still, solitons may exist due to the interplay of all other terms, and for them, so they will be principles described by the same set of analytical expressions, and then one can also analyze the stability. For the solitons, actually, the stability region is, in some sense, it is larger than for the solitons in the case of the self-focusing. It's the same plane of the same two control parameters, which are gamma naught, the strength of the linear gain in the active core, and the strength of the filtering in the same active core. We have this extended stability region for the dissipative solitons in the case of self-defocusing. And finally, there is one more possibility. Let us look again at our underlying system. We may have still one more possibility. What we can do, so here we had this coefficient with 1/2. 1/2, this is the coefficient of the group velocity dispersion. We assumed it is usually done in fiber optic, that it is anomalous dispersion, so it's positive, and by scaling it's equal to 1/2. But we can consider a different model when we, by definition, take the case of the zero dispersion point. So by definition, we take carrier wavelengths at which the dispersion coefficient vanishes, such a zero dispersion point always exists. And if we want, we can write the equation exactly adjusted for this case. So this means that it will be essentially the same model, but instead of coefficient 1/2, we have 0, no dispersion term. All other terms are present. And in that case, still, even without the group velocity dispersion, the system admits exact solutions for the dissipative solitons, and there is some finite stability area for these solutions in the parameter space. So let me remind that this was a stability region when we have the anomalous group velocity dispersion and self-focusing nonlinearity. this is the stability region when we have the anomalous group velocity dispersion and self-defocusing nonlinearity. And now we have the case when, by definition, the group velocity dispersion is absent. In that case, actually, the sign of the nonlinearity doesn't matter because the solutions will be essentially the same for self-focusing and self-defocusing. And then we still have a finite stability region. But now the stability region is shown in the plane of a different set of parameters, which is more relevant in this case. One is gamma naught, small gamma naught. Small gamma naught is the gain in the active core, and capital gamma naught is the loss. And in the passive core. And then, moreover, if we have a stable dissipative soliton in the system, one more thing that can be studied, this time, of course, numerically, this is interaction of two such solitons. So we can create, for example, a pair of solitons at some distance from each other and let them interact. So here, typically, usually when people study the interaction of solitons, they consider the pair of solitons with the phase shift, phase difference is a 0 pi. In the case of the conservative nonlinear Schrodinger equation, zero difference of pi implies that two solitons repel each other, and the phase difference of 0 implies that they attract each other. In this dissipative model, the result of the interaction is essentially the same for either sign for both cases. When we have the initial phase shift 0 pi, what they do, they effectively attract each other, and they merge. These two dissipative solitons merge into a single dissipative soliton, simply merge. And then, moreover, one can take the input for the group of three dissipative solitons, and what will happen? This cluster of three solitons will be split in essentially in the bound state of two solitons and the separating free soliton, which actually is moving in another direction. Then this type of the system, which predicts is sometimes analytically, sometimes numerically stable dissipative solitons in the cubic, in the coupled Ginzburg-Landau equations with the usual cubic nonlinearity without the exotic quintic nonlinearity. So the analysis was generalized for some other situations. For example, here it's possible to study numerically the situation where, strictly speaking, we do not satisfy the condition for the stability of the zero background. So the background, the linear background, the zero background is unstable, but the instability is weak, and therefore the background, the solution in the unstable background does not blow up. It simply develops some random floor, so to say, random background with random fluctuations. And then one can numerically construct a solution. It will be a tall, narrow soliton on top of this finite amplitude background with random fluctuations. And then what is observed is essentially as a result of the dynamical simulation, this will be a random walk of this. The soliton is essentially a robust object. It's essentially stable. And due to the interaction with a randomly oscillating background, it demonstrates some random walk. Then some applications of this configuration to optics were proposed. In particular, this is the simplest system. It does not include any gain whatsoever. It just includes the coupling, and it only with the loss in the passive core. So of course it cannot support any soliton because it doesn't operate. Filters are necessary in many cases in order to remove the random optical noise, and this is exactly what can be done here. The random noise, due to the parallel lossy core. In the parallel lossy core, it will be absorbed by the action of the linear loss. So this is some illustration how it operates. So it's actually strongly an input is taken in the form of the inputs, optical solitons, with a very strong element of randomness, and after passing this filter, this set of inputs will be essentially not completely, but will become much more coherent than it was originally. On the other hand, a similar configuration can be used also as a model of the nonlinear amplifier. So the model is similar to what we discussed today. But now it can be used. It can be used now when we have the strong gain acting as the active core. Because it's too strong, it will not be able to support stable solitons. But here the objective is different. The objective is to have an optical element which will not amplify weak signals, but will amplify strong signals. And such a nonlinear amplifier is necessary in various setups which aim to produce eventually stable solitons. So a part of the setup to produce a stable soliton is exactly nonlinear amplifier. Why nonlinear? Because it should not amplify the random noise. It should amplify only the soliton, the solution with non-zero amplitude, but should not amplify random noise added to it. And so this configuration was demonstrated. It can be used eventually to design such a particular type of the nonlinear amplifier. Then one more possibility, it can be a similar configuration can be developed for the two-channel system. Two-channel system means that we have a dual co-fiber, and in each fiber we now consider co-propagation of two optical waves. Sometimes it may be two waves with different carrier wavelengths, or sometimes it may be co-propagation of waves with different polarizations, mutually perpendicular polarizations of light. So in that case, some analysis. So now it means that we should have a system of 4 equations, because in each core we have 2 amplitudes with the 2 co-propagating optical modes, and then we have and the number of cores is 2. So we will have system of 4 equations. Of course, it has many coefficients. It's more complex. Nevertheless, it can be analyzed, and the existence of stabilized dissipative solitons, which have their components in co-propagating channels, can be also demonstrated. And then one more possibility is that a similar scheme can be applied to a different type of nonlinearity, not cubic but quadratic. So this is we had a chance once to discuss it. It's another type of the optical nonlinearity, which takes place not in materials such as amorphous silica, not in isotropic materials, but in optical materials with intrinsic anisotropy, optical crystals essentially. In that case, due to the anisotropy, we may have the generation of the second harmonic, which means that we will have the not cubic but the quadratic nonlinearity. Okay, so this is a system of such rather standard model. U1 is the amplitude of the fundamental or first harmonic, and U2 is the amplitude of the second harmonic. So we see what we see here, the square of the fundamental harmonic is the source which generates the second harmonic. On the other hand, we have here the usual parametric interaction. It means that, roughly speaking, one photon of the second harmonic may split into a pair of solitons as the fundamental harmonic. So now, if we are interested in the problem of stabilization, we can add the third equation here. It's enough to couple it only to the fundamental harmonic. It's not necessary to have a similar dissipative component which would couple to the second harmonic. And then if we have such a system of three equations, what we have now, we have the linear coupling between the active component of the fundamental and the lossy component of the fundamental. We have this linear loss acting on the passive component. Simultaneously, we have the linear gain acting on the active component of the fundamental. And together, if we analyze this, we will see that this system of three equations, we will not find the exact solutions, but it will be possible by means of numerical methods to demonstrate that it supports completely stable dissipative solitons, which are supported by the quadratic nonlinearity. So these are solitons in the second harmonic generating system, and which are made stable in the presence of the gain by means of the stabilizing loss, which is applied in the linearly coupled component. Okay, so what remains is 1 minute. And let me just use a couple of minutes to very briefly mention the next step which can be done in the development of this type of models. It's possible to consider also linearly coupled system with the so-called with the gain and loss, but now with a strictly balanced gain and loss. So the amount of gain in one core, in the active core, would be exactly equal to the amount of loss in the parallel core. And this is called, usually such a system with exactly balanced core and gain is called parity time, or for brevity, PT-symmetric system. So similar to what we discussed today, the simplest model of this type is written here. Without this term with I, it would be the model that we discussed more than once. It's the conservative model for the coupler, dual core optical fiber. And now we have the parity time symmetry means we have with exactly the same coefficient gamma, we have the linear gain in one core and the linear loss, exactly equal linear loss in the parallel core. And then what is interesting, it's possible to demonstrate in the purely analytical form. In the purely analytical form, we can first of all find exact soliton solutions for this case when we have the balance between gain and loss. So this will be actually the exact soliton, is a parity time symmetric soliton. Its component V and U are coupled by this relation, which depends on this gain-loss coefficient gamma. And eventually, what is really interesting, I mentioned sometime before in the context of a different topic, that when we have this traditional conservative system without gain and loss, we may have it's possible to analytically find the limit of destabilization of the symmetric soliton with respect to the spontaneous symmetry breaking. So this threshold of destabilization of the symmetry of the parity time symmetric soliton with respect to the spontaneous breaking of the symmetry can be also found analytically in this system, and the eventual result is written here. So it is essentially the amplitude of the soliton. So if it's simply 4/3, this is the result that we had a chance to discuss previously, is the threshold above which, if the amplitude is larger than this, the symmetric soliton will become unstable against spontaneous symmetry breaking. Now, this is a modification of this result in the presence of the gain and loss. If you have the PT symmetry, the common coefficient of gain and loss must be smaller than 1, which means, physically speaking, that gain and loss should be in balance with each other, and they should be smaller than the effect of the linear coupling. Otherwise, everything will be destroyed. And then if this condition holds, we have this reduced exact result, which shows the instability threshold, the stability boundary of the onset of instability for the PT-symmetric soliton. So previously, when we studied the conservative version without gain and loss, the conclusion was that above this threshold, the unstable symmetric soliton would be replaced by a non-trivial stable asymmetric soliton. In the case of the PT symmetry, it's not possible. If we break this condition and the PT symmetric soliton is no longer stable, the instability will actually give rise to the explosion, to the blow up, because then if we break the symmetry, the gain and loss will no longer be balanced, and then either the gain will become stronger and the system will blow up, or the loss will become stronger and the system and the solution would decay to zero. So here only, if solitons exist, they may only exist as a PT symmetric solitons. And then what is really interesting, we can find the exact analytical solution for the instability boundaries. So just the last thing to show, this is the illustration. So this is a numerical verification of this. This is analytically predicted stability boundary, and this is its numerically found counterpart. In this simulation, they are not identical because of the finite accuracy of the numerical scheme. But essentially, it can be checked that indeed we have the correct exact analytical prediction for the instability boundary of these PT symmetric solitons. We can also have anti-symmetric solitons, PT anti-symmetric, when U and V, two components, are not proportional to each other, but proportional to each other with sign minus. In that case, the final result will be they all are always unstable. Okay. I think that last remark about this, okay, because if we have stable PT symmetric solitons, we can consider their motion, and then we can, because the system is still Galilean invariance, we can have moving solitons, and then why not to study collision between them? So they can normally they can collide elastically, similar to solitons in integrable systems. Of course, this system is not integrable. Nevertheless, the simulation of the typical collision demonstrates that the collision remains quite elastic, and this is a typical result. Typical result of the collision. Okay, so here I should really stop because today we have no more time. The next related topic would be to consider a two-dimensional version, where this mechanism of stabilization for the dissipative soliton may also work, but hopefully we will have a chance to do it sometime later, maybe in another semester. And here I should complete the lecture for today. Thank you very, very much for your interest. And as far as I understand, this is the last lecture in this cycle.
Okay, thank you very much, Boris. Yes, this is the last, today was the last day for the lecture of this cycle of lectures.
Mm-hmm.
Yeah, depending on the situation, for the moment, I cannot say whether we continue in next semester or not.
Okay, it's, of course, it's
but
up
anyway,
to you.
I will let you know if there is a possibility to continue with our lectures.
Yes, definitely.
Okay, thank you very much again.
Okay, thanks to everyone. Thank you, Emmanuel. Thanks to all participants of these lectures. I hope you can hear something interesting.
Okay, thank you.
Okay, bye-bye.
Bye-bye. Bye-bye to everyone.
Bye-bye to everyone.